Hello, welcome to Chapter 9, Homework Questions 50 through 55. Question 50. Solve the problem below by writing and solving an equation. Be sure to define your variable. There are a total of 122 countries in Africa, Europe, and North America. Europe has twice as many countries as North America, and Africa has 7 more than Europe. How many countries are there in each of the 3 continents? Write an equation and solve it to answer this question. All right, so we want to make sure that we define our variables here. We have 3 different things happening, or 3 different continents. We've got Africa, Europe, and North America. So Europe has twice as many countries as North America. So let's let N equal the countries in North America. All right, and so based on this statement, Europe has twice as many countries as North America, then we know that 2 times N, or 2 times the number of countries in North America, is equal to the number of countries in Europe. And then as we read on, it said Africa has 7 more than Europe. Well, Europe has 2N, so then we know that 7 more, we add 7 to the number of European countries, and we have the number of countries in Africa. And so now that we have kind of defined all our countries, the number of countries in each of the continents, how many countries are in each of the 3 continents? Well, we also know that there are a total of 122 countries in all 3 of them. So we can set up an equation to say that the number of countries in North America plus the number of countries in Europe, so N plus 2N, plus the number of countries in Africa, which is 2N plus 7. So I'm going to put parentheses just so you can see the 3 different ones, should equal 122. And so now we can combine our like terms, which would be 5N plus 7. Subtract 7 to both sides. 5N is equal to 115, and then divide by 5. So we get N equals 23. It does want to know how many countries are in each of the 3 continents, so we need to answer all 3 questions. So we know that N is equal to 23, so we know this one's 23, North America. 2 times that would be 46, so there's 46 countries in Europe, and then if we add 7 to the number of European countries, we have 53. And then make sure you do answer the question. Just putting those numbers there is not good enough. You really need to make sure that you are answering the question completely. So 23 countries in North America, 46 countries in Europe, and 53 countries in Africa. Question 51. Solve each of the following inequalities for the given variable. Represent your solutions on a number line. So part A, we have 2 times the quantity 3p plus 1 is greater than negative 4. So we're going to solve this. I'm going to go ahead and distribute the 2, but we're going to solve this for the boundary point. So we're going to set it equal to negative 4, subtract the 2, divide by 6, and we get p equals negative 1. So that's our boundary point. So on my number line, we have 0 and then negative 1's here. So we know it's an open circle because it's not included, it's not equal to, it's just greater than negative 4. And then we have to figure out, are we talking about values less than negative 1 or greater than negative 1? So I'm going to test the point x equals 0. Plug that into the original. 2 times 3 times 0 plus 1. Is that greater than negative 4? Or 2 times 1? And we find out that 2 is greater than negative 4, so this is a true statement, which means all of these values on this side of negative 1 will be solutions. So what are those values? Well, these are the values of p that are greater than negative 1. So all of this is part of your solution because it wants us to solve and also represent your solutions on a number line. So you need both parts. All right, let's look at B. So B, we have 9k minus 2 is less than 3k plus 10. So we'll start by finding the boundary point by solving this inequality as an equation. So I meant to change it to equals. So 9k minus 2 equals 3k plus 10. We will subtract 3k, get the variable on one side. 6k minus 2 equals 10. add 2 to both sides. 6k equals 12, divide by 6, k equals 2. That's the boundary point again. So on the number line, here's 0 and here's 2. It's either an open or closed circle. This one, once again, the inequality does not include equal to, so it is an open circle, and then we want to test a point. I try to test x equals 0 as long as it's not the boundary point. Usually it's the easiest one to plug in because so many things cancel. So 9 times 0 is 0, and then on the other side, 3 times 0 is 0. So all you're left with is negative 2 is less than 10, and that is a true statement. So we want the values where 0 is, which is to the left. So since 0 was true right here, that's where the solutions are going to fall. And once again, don't forget to write the inequality as well. K is less than 2. So all of this, again, is part of your solution. And then on to part C. C is 5 minus h is greater than or equal to 4. So 5 minus h is equal to 4. Once again, looking for that boundary point. We could subtract the 5, and that would give us negative 1. Divide by negative 1, and h is equal to 1. So we know, once again, our boundary point is at 1. Is it an open or closed circle? This one does include the equal sign, so it is part of your solution. So we do need to have a closed circle here. So 1 is a solution. If you plug that in, you'll get 4 is greater than or equal to 4, which is true. And then once again, we need to test some value that is not 1. So I'm going to test x equals 0 again. Plug 0 in for h. 5 minus 0 is greater than or equal to 4. 5 is greater than or equal to 4. That is a true statement. So we will go in that direction of the 0. Now, on all of these, it looks like they just so happen to be true on the point that I picked. But if you pick a point that is on the other side, you will find out that it is false. And if it's false on that side, then it's going to be true on the other side. So you know which direction to go. And so our inequality is all values of h that are less than or equal to 1. Problem 52. Solve the following quadratic equations. Check your solutions if possible. On 52, it doesn't tell us what method to use, so we can use any method that we want to solve. On the first one, 2k squared plus k minus 6, my first instinct is to try and factor it. It's already set equal to 0, so let's check to see if it is factorable. We have a 2k squared and a negative 6. So are there factors that multiply to give you negative 12k squared that are going to add to give you 1k? And there is. It would be 4k and negative 3k. So it is factorable. So I'm going to go ahead and plug those in and factor out, or factor the side lengths, figure out what those are of the rectangle. So 2k and k, that means this would be a plus 2, and that would be a minus 3, which would still give us a negative 6. So it does factor to 2k minus 3 and k plus 2. Now that's just the factoring. We have to use the zero product property. So that's the method I used on A. Set your factors equal to 0 and then solve for k. So add 3 divided by 2, that's 1.5. Subtract 2, that is negative 2. So k is equal to negative 2 comma 1.5, or you can just say or in between those two. Either one's fine. And it does want you to check your solutions. I'm not going to check them on here. You just have to plug them back in to figure out whether they are correct or not. B, m squared is equal to 9. So this one, you might subtract the 9 first, which is perfectly fine. That is equal to 0. And you might recognize this as being factorable because it is a difference of squares. You also might have recognized that you could actually go ahead, because you don't have that middle term in m squared, you can take the square root of both sides, and that would give you the absolute value of m is equal to 3. And so you have m equals negative 3 or m equals 3, and you're done because you've solved for both of those. So that's another way to do it. But it also could have been done using factoring. Either one, once again, is fine. You can choose what method you want to solve these problems. On to C. C, it is in factored form, but it's not equal to 0. So we're going to distribute the W inside the parentheses so that we can factor it correctly if it can be factored at all. So this would be 2W squared plus 8W, and then I'm going to actually subtract the 24 to the other side. So that would be minus 24 equals 0. I'm going to go ahead and once again try to factor it because it looks nice enough that I could do it. I did notice that there is a 2 in common, so I'm going to factor the 2 out. That's going to leave me with W squared plus 4W minus 12. And then we need to figure out, can it be factored? So we have W squared and negative 12. So are there any factors that multiply to give you negative 12W squared but add to give you 4W? And it looks like we could do 6W and negative 2W. So that looks like it would work. So we'll put the 6W and the negative 2W, and then we would have W plus 6 on the top and W minus 2 on the bottom. So it does factor. We have 2 times W minus 2, W plus 6. So once again, we could use the zero product property on this one. Set our factors equal to 0. Now we do have a factor of 2. 2 will never equal 0, so it's not going to give you a solution. You're only going to get solutions from the variables. So if we add 2 and subtract 6, we have our solutions as W equals negative 6 comma 2. And so we could have solved it using the quadratic formula possibly as well if you didn't see that it could have been factored. And then on B, I really used completing the square or square root on that one. And on to the last one, D. Now D is not equal to 0, so probably want to subtract 5 to both sides. 3n squared minus 4n minus 5 is equal to 0. And once again, the numbers are nice enough that we can at least look at the possibility of factoring. This would be 3n squared minus 5. So are there any factors that multiply to give you negative 15n squared but add to give you negative 4n? 5 and 3 won't work, and 1 and 15 won't work. So it looks like it's not factorable. So since this is a 3n squared, we don't want to use completing the square. So it looks like we're going to be using the quadratic formula on this one. So remember, the quadratic formula is x equals the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. Let's identify what a, b, and c are. A is the coefficient of n squared, b is the coefficient of n, and c is the constant. Now we can take those values and plug them into the quadratic formula. So we have x equals the opposite of negative 4 plus or minus the square root of negative 4 squared minus 4 times 3 times negative 5 divided by 2 times 3. So simplify. Opposite of negative 4 is 4. And then plug all of that into your calculator. You can do it in parts, but you're going to get 16 plus 60. 16 plus 60, which should give you 76 underneath the square root. And so now we have two answers. We have x equals 4 minus the square root of 76 over 6, which is approximately some value we'll figure out in a second, and x equals 4 minus, or plus, the square root of 76 over 6, and figure out what that value is. So plug that into your calculator. Make sure that you are taking 4 minus the square root of 76, get that answer, and then divide that by 6 so that you are getting the accurate and the correct answer. And so when I plugged that in, I got approximately negative 0.79 and 2.12, which means it wasn't factorable, so it just kind of proved that we did do that correct up there. And then you can see I wrote my solution right there. So once again, on this problem, it just said solve the following quadratic equations. Check your solutions when you can. I was really able to use factoring on A, B, and C, or the zero product property. Used a form of completing the square on B, though. And then D, the quadratic formula is definitely the best option on that one. Question 53. Identify the statements below as sometimes true, always true, or never true. So on question A, -4 is less than or equal to 9. So when you're looking at these problems, there's no problem in terms of creating a number line to help you identify whether something is true or not. So -4 is definitely less than 9, so this is always true. B, x is less than 1. Well, depends on what x is. So any values less than 1 are to the left of 1. So as long as we have that, we have numbers that work sometimes, and we have sometimes numbers that don't work. So this would be sometimes true. It depends on what x is. -5 is greater than -2. So -5 is here, -2 is about here. So compare -2 and -5. -2 is greater than, or -5 is less than. So this is never true, because -5 is less than -2. D, we have 3x plus 5 equals 2. So you could solve D if you needed to by subtracting 5 and then dividing by 3. And so x is equal to -1. So it's true when x is equal to -1. It's not true when x is equal to any other number. So then therefore this is sometimes true. Most of the time it's not true, but it's only true when x is -1. E, 61 is equal to 61. This is always true. And those two values are always the same. And F, -6 is less than -6. -6 is not less than -6. It's equal to -6. So this will never be true. Question 54. Robbie builds model rockets. One day he sets up a rocket, backs away from the launch pad, and then shoots the rocket off into the air. The rocket's path is represented by the equation y equals -10x squared plus 130x minus 400, where y is the height in meters off the ground and x is the horizontal distance in meters from Robbie. So 2 parts. A, use either the zero product property or the quadratic formula to find the x-intercepts of the path of Robbie's rocket. What do the x-intercepts tell you? And then when Robbie's rocket lands, how far is it from the launch pad? So just to kind of get a visual in terms of what's happening here, we have our x value, which is our horizontal distance, and our y value, which is our vertical distance. So the rocket starts on the ground at 0, 0. And when it's launched, it goes up and it comes back down. So the x-intercepts are going to represent where the rocket started. Now, I've said it started at 0, 0. It doesn't necessarily start there, but it is going to have 2 x-intercepts, where it starts and then where it kind of falls to the ground. So let's either use the zero product property or the quadratic formula. The numbers are a little bit larger here, but the other thing I notice, which might make it easier to potentially factor and use the zero product property, is all those numbers have a factor of 10. So this is really, we're solving for when y is 0. So if we divide everything through by -10, that will give us positive x squared minus 13x and then plus 40. Now that's a little bit easier to look at to see that maybe we can factor this. So let's look at factoring. If not, we'll use the quadratic formula. So what are factors of 40x squared? What multiplies to give you 40x squared but adds to give you -13x? So we got 1 and 40, 2 and 20, 4 and 10, and 5 and 8. So it looks like -5x and -8x would work out. And so then our side links, we have x times x, and then we'd have x times -8 and x times -5. So it looks like it does factor nicely. X minus 5 times x minus 8 is equal to 0. Use the zero product property to solve, and we get x equals 5 and x equals 8. So going back to answer part A, it wants us to find the x-intercepts. So the x-intercepts would be at 5, 0, and at 8, 0. So it does say back in the original part that the x is the horizontal distance in meters from Robbie. So if the first intercept is at 5, 0, then that means Robbie must have backed up 5 feet from the rocket, because that's the distance from Robbie. And then the 8, 0 is where the rocket landed. So it landed 3 feet, or actually 3 meters, sorry, beyond its original point. So I went ahead and explained that right there as well. Robbie backed up 5 meters from the launch pad, and the rocket landed 8 meters from Robbie. So that's what those two x-intercepts represent. Once again, because it does say that x is the horizontal distance in meters from Robbie. So the rocket is 5 meters from Robbie when it launched. B says, when Robbie's rocket lands, how far is it from the launch pad? So remember, I'm going to change my graph here a little bit because it's a little misleading based on the information. So we would say Robbie's here, and then here at 5, 0 is when the rocket launches and then comes back down at 8, 0. Okay? So when Robbie rocket lands, how far is it from the launch pad? Well, the launch pad is right here. Okay? So how far is it from the launch pad? Well, that would be 3 meters is how far the rocket lands from the launch pad. And Robbie is 5 meters away from the launch pad itself. Question 55. For each parabola graph below, visually estimate the x-intercepts. Then use the quadratic formula to confirm your estimates. So on part A, it looks like these are going up by ones. So 1, 2, 3. So somewhere in between 0 and 1. So I'm going to approximate it. It looks like it's a little bit more than a half, maybe like 0.7, 0.8, something like that. And then this is at 4, so it's in between 4 and 5, a little bit closer to the 4, so we'll approximate it at 4.2. But now let's actually use the quadratic formula to see how accurate those guesses are. So negative b plus or minus, or the opposite of b plus or minus, is square root of b squared minus 4ac, all divided by 2a. And a is equal to 1, that's the coefficient of x squared. B is equal to negative 5, and c is equal to 3. So those are the values we're going to use to plug into the quadratic formula. So the opposite of negative 5 plus or minus the square root of negative 5, that quantity squared, minus 4 times 1 times 3 divided by 2 times 1. If we simplify that, that would be 5 plus or minus the square root. Looks like that's going to be 25 minus 12, so that's 13 divided by 2. And we can separate it into our two parts. We have x is equal to 5 minus the square root of 13 divided by 2. What does that approximately equal? And x is equal to 5 plus the square root of 13 divided by 2. And what is that approximately equal to? So you can plug that into your calculators and see what you get. And so there are the two answers that I got. So it looks like x is approximately 0.7 or 0.70, depending on how many places you decided to go out to, and 4.30. So I was a little bit off, as a tenth off on both sides there. But in terms of where it was on the graph, we could tell it was somewhere in between 0 and 1, but closer to 1. All right, let's take a look at B. So B, once again, if we're going to make some guesses here, this is 1 and 2. So we could say that we think it's going to be approximately between 1 and 2, a little bit closer to the 2 side again. So let's go with maybe 1.6 on this one. And then on the other side, we have negative 3 and negative 4. Closer to the negative 4, but bigger than negative 3. So let's go negative 3.6 on this one as well, maybe negative 3.7, somewhere in there. But let's use the quadratic formula and find out a little bit better how our guesses are. A is equal to 1, B is equal to 2, and C is equal to negative 6. So x equals the opposite of B plus or minus the square root of b squared minus 4 times a times c divided by 2 times 1. So that looks like we'll get 2 plus or minus, negative 2, or opposite. So 2 plus or minus the square root. That's going to be 4 plus 24, so that's 28 over 2. All right, and so now to get our approximations, we'll plug in x equals negative 2 minus the square root of 28 divided by 2 and figure out what that is approximately, and x equals negative 2 plus the square root of 28 divided by 2. So plug that in the calculator and see what you get. So I got negative 3.65 and 1.65 as my solutions. I went out to 2 decimal places, but my approximations were better on this one. I had 1.6 and negative 3.6, so very close to what I had there. If I would have rounded to the nearest tenth, it would have been the same. So, but there's 2 examples in terms of solving using the quadratic formula.